It won't take much longer than about 20 minutes. There is no assignment this week. However, so operating systems, some of the topics we'll talk about today, we discussed last time. And hopefully some of these you kind of have an idea about. So it shouldn't be all entirely new. If it is, that's fine. But from last class, we talked about memory, we talked about processors, we talked about what their purposes are. So this should be a bit of a refresher from last time, or last Wednesday anyway. All right, so the operating system, it sits between the hardware and the user, okay? So operating system is like Windows, it's like Mac, and then it's like Linux. What those systems are responsible for, and really all they are a big collection of programs, individual programs, or in Linux case, it's one huge program. But it's responsible for allocating memory and swapping memory from your RAM to your storage to the cache. It's responsible for scheduling what different processes should be run on the processor. Right, so I have PowerPoint open and I have Google Chrome open. So the operating system is responsible for scheduling between the two on my CPU. It's also responsible for interpreting the different signals from your I/O devices, such as your keyboards, your mice, your speakers, your headphones, your webcam. The operating system is responsible for receiving all those different signals, interpreting them, and then responding in how you expect it. For example, if I click my mouse, the operating system receives that signal, processes the signal that, yes, the mouse was clicked, and then it calculates where on the screen or where in the program I clicked and what should happen as a result. The basic elements of a system or operating system, of course, you have your processor, your I/O modules, which are incredibly important because if you didn't have those, there's no way for a user to interact with the system. You have your main memory, which is your RAM, and then you have your system bus. The system bus is responsible for making that communication channel available between your processor, your I/O modules, and your main memory. So if you look here, everything, every device, every component connects to that system bus. And through that system bus, they can communicate. So your I/O devices send the signals through the system bus to the CPU. Your CPU uses the the system bus to retrieve data from memory, from storage, and so on and so forth. So the system bus is critically important because it provides that backbone communication channel for the computer as a whole. So the processor, again, we talked about this last time, but it controls the operation of the computer. It receives all those machine code bits, the binary machine code, interprets that, and then responds as a result. It performs the data processing functions, referred to as the CPU. All right, we have our RAM, or our main memory. So like I said last time, your running programs are stored into RAM. For example, I have PowerPoint open, I have Google Chrome open. Those are loaded into RAM. And if you don't know how to see the utilization of your computer, if you go down here to the taskbar, right click, open Task Manager, this will come up. And from here, you can see your CPU utilization, how much memory is being used. So I have Google Chrome, Excel, PowerPoint, Notepad, Windows, Zoom. How much of your disk is being used, so your hard drive or your SSD. Your network, how much of your GPU is being used. And as you can see, Zoom is actually eating up about 10% of my GPU just from running this video, processing this video, and recording. All right. We have our I/O modules, so our communication devices, communication equipment, our networking devices. our secondary memory devices, so our disks, and then our terminals. So um, in the past, computers were essentially, you would have a terminal here locally, but then the actual computer would be somewhere far off, and you would just connect to the computer. Similar to having a PuTTY session or a SSH session to a server somewhere. And PuTTY SSH, all that is you're opening a command line locally on your computer. So command line is this, right? So for example, I open this command line, but really I'm connected to a computer that can be geographically separated from me. So for example, I have the website server, which is a Amazon server that is, I think, located in Virginia. But I use a command prompt or command line to connect to that server and go from there. And I control everything on that server from here. Same thing as what a terminal essentially is. We have our system bus. Again, it provides that communication channel for the processor, the main memory, and your I/O modules. The microprocessor, this has seen a lot more popularity recently because of the popularity of mobile devices. And then we have our multiprocessors, which we provide more cores on one single chip. This is popular because of concurrency. That's a term that you use when you talk about running programs simultaneously. So you say you're running them concurrently. And this is popular because, like I said, I have Zoom open, I have PowerPoint open, I have Excel open, and I have Google Chrome open. Well, historically, if I only had one core on my processor, I'd have to run each one of these programs sequentially. So if I'm using PowerPoint, Google Chrome isn't working. You know, I'd have to stop PowerPoint, open Google Chrome, or it would be very slow shifting between the two. However, with multi-cores, I can run all these different programs concurrently, simultaneously, and with very little latency or delay. Another popular device or CPU technology is a system on chip. This is where the CPU is soldered permanently onto your motherboard, and it cannot be removed unless you buy a whole new computer. This is used in embedded devices like Raspberry Pis or Amazon Alexas, and even cell phones. They use system on chips. So here you'll see a Raspberry Pi. This Raspberry Pi has a CPU soldered onto the board. And that CPU is not built to be removed or replaced. If you want to replace the CPU, you have to get a new Raspberry Pi. Same with a cell phone. You can't upgrade your CPU on your cell phone. You have to buy a whole new cell phone. However, with desktop PCs, desktop motherboards, right there is a socket for your CPU. You can remove and upgrade your CPU as technology progresses, as long as your motherboard is compatible with that new CPU. So that is helpful for the modularity of a desktop PC. Right? You can swap different components and keep your PC up to date without having to replace every single thing of your PC. And just like I talked about last class, these different slots are for your different devices and RAM. So your GPU would go right here. Your RAM and main memory would go here. Your CPU would go here. Your I/O panel is usually up here, so on and so forth. All right, so memory hierarchy. Again, we talked about this last time as well. As the memory gets faster, so your cache, your register, your main memory or your RAM, your solid state drive, your hard drive, and then you have magnetic disks. As it gets faster, it also gets more expensive per bit. So you have those financial constraints when it comes to your different levels of memory. However, we have these different levels to speed up the processing of a PC. If everything ran off a hard drive, our PCs would be incredibly slow. However, we have these different hierarchies and levels of memory so that the processor can access different bits of data a lot faster. So again, the relationship, faster access time, but greater cost per bit. You have, on the flip side, you have greater capacity and a smaller cost per bit. However, with greater capacity, it's also slower access speed. Here's the different memory hierarchies. We have our registers, which are on the cores. We have our cache, which can be shared across the different cores on a multi-core CPU. We have our main memory. Then we have magnetic disks, CD-ROMs, DVD RWs, DVD RAMs, Blu-rays, and then we have our magnetic tapes. So magnetic tapes, they're typically used for offline storage, or cold storage is another term for that, where you're not really trying to access this data frequently. Think, for example, historical newspapers, right? Or newspaper clippings, newspaper articles. They would store those on a magnetic tape and then put it in a storage locker somewhere just to hold indefinitely. Magnetic tapes retain their data for a very long time. It's hard to corrupt that data. However, it's very slow, so if you're trying to access it, don't expect it to be quick. That's why it's typically used for offline storage. Like we talked about last class, we have a cache memory, which can be shared across the cores. It's very, very, very fast. However, it's very expensive. And so usually only frequently accessed data is stored into cache. And this is there's a diagram of how cache, CPU, and main memory all relate to one another and work with one another. So our CPU only reads from cache. However, it can go to main memory and try to load data from main memory into cache so that the CPU can access it. In a 3-level cache system, of course, we have 3 levels of cache available to us, and these can be shared across the different cores on a CPU. So cores can share data. So now, again, here recently, we have multi-core CPUs. This is much more popular because of concurrency. We can run programs simultaneously. And we like to multitask. We like to run a lot of different programs without even thinking about it. For example, on a cell phone, you can have 52 apps open simultaneously, and the CPU is responsible for switching through that. Actually, the operating system is responsible for switching or scheduling those different processes and apps onto the CPU. However, that does drain power, that does drain battery life, having that many apps open, having that many programs open on a computer. It also uses up a lot of CPU and memory as a result. And that'll do it today. So next time, like I said,